All right, all right. So welcome back to this YouTube video. So in the last video, I have you have learned about time series data, how we can manage with the time series data, and what is time series data, and then we have also performed RNN, a special type of neural network architecture to to find stock price detection, to actually find relation between stock prices, and learning about how to forecast stock prices and all that. So in this video, in this we are going to solve a problem of RNN. So there is a very famous problem in the time series forecasting field or state of the art. So there is a problem called vanishing gradient. I'm going to first tell you what that problem is. I have also hinted you about the problem in the last video. I'm going to elaborate it further, and then we are going to look at a solution, which is a solution to some extent, but later attention mechanism was developed. So first we'll learn about RNNs, what they are, how we can. Yeah, in this video we are going to learn about LSTMs and GRUs. They will somehow solve this problem of vanishing gradients. We are going to discuss about that in this video. Okay, so let's start. First, I'll tell you about the problem, what vanishing gradient problem is. So this is called, sorry. No, the problem, sorry, what is happening? Okay, so what is vanishing gradient problem is? So let's say there is a sequence, there is a sequence of values, or probably let's say we have a graph that goes something like this. Okay, so let's say that we have a sequence. Think about that. So we have this sequence. We have this good sequence. So let's say there is some features here, and then let's say we are doing some classification. Let's say this is some text. Let's say this is some text, and we want to classify if this text is no, um, let's say we want to classify if this text is um, a toxic or not. All right. So if you want to classify if this text is toxic or not, so let's say there is some features here. There are some features here that says that the text is toxic. So let's say there are some words here uh, that may hint us that the text is toxic. And let's say we are at the end of sentence, we have lived it all of the sentence, and let's say there are some let's say this text is already neutral, and there is no features here. Let's say this is the only feature that we can, based on that we can classify the text is toxic, let's say. So the problem is, if you use an RNN, let's say this text is very long. There's some hint and some features and some gradient in the starting of the text. RNN might not be able to uh, catch that. RNN might not be able to catch that because you know as we perform more and more calculations, as we have more and more weights and more calculations, more and more outputs and more hidden states, we might forget this, and this gradient might get very small. So thus we get the name of vanishing gradient. So this gradient of this text will get smaller and smaller, hence we might not be able to predict the actuality, and we might not give that much importance for this specific word or this specific gradient. So that is the problem of vanishing gradient. So the inability of the model, the RNNs, to not be able to detect that features, right? So if you just write the formulas of RNN, we'll get it. Let's say we have we will just predict using the previous. We'll use the previous hidden state. We'll get the previous output, and we will just do the calculation w into x, the current input, plus the w into the previous hidden state, and we'll add the bias, right? So we might not be able to give importance to the important features. So RNN cannot find the important features, what the important features are. So in the GRUs or in the LSTM, that is a problem that we are solving, and that is why they are better to some extent. This is the GRU, right? And then this is the LSTM. I'll explain you what is happening here. First, as you might see, we have two sigmoid functions, right? So we have two sigmoid functions. Just forget about the tannage. I think like you can use whatever activation function at the output layer you want. Based on the problem that you are solving, you can use the activation function that you want at the output layer, right? So we have two sigmoid functions. So this is sigmoid, by the way, if you don't know. So this is sigmoid, and then we have two outputs that are so what is sigmoid function going to do? Well, whatever output we are going to get, the sigmoid function is going to convert this output between the range of 0 and 1. So the output is going to be between 0 and 1. So we are going to have Z and R. So here W, U, and B are weights, as you might know. WZ, WR, WH are weights, and then UZ, UR, and UH are weights. BZ, BR, and BH, here it is H, are weights. Right? Easy things, right? Now what we are going to do is at every step we are going to have these weights, and it's almost identical. We'll just multiply this weights WZ with X of t, the current inputs. If we don't have current inputs, then we can just not include these terms. We don't have to use these terms if we don't have the current inputs to our current RNN unit or current neural network. So remember, this is just like I'll just make sure to. So as I've told you, we'll have these boxes, right? The boxes of information flowing, and then we'll get the inputs, let's say the X of t's, and then we'll get the final outputs, probably something like that, right? So we are going to have gradient shifting. So each units in the case of GRUs is going to contain, wait, so this, okay, wait a minute, I'll share the screen. So each unit is going to contain this calculations. Each unit is going to perform these calculations, and every unit are going to have the same structure and the same weights. So yeah, we are going to have perform this function. We are going to get h of t minus 1 is nothing but the previous hidden state. We are going to get the current input and multiply that by a weight wf, and then we are to get the sorry for that. We are going to get the current input, multiply that by wz, get the previous hidden state. We'll get the hidden state from the previous unit. We'll multiply that by uz, and then we'll add bz. Is nothing but the bias. We are going to do that same for both of these sigmoid functions. Actually, they are identical except the weight matrices, and then we are going to calculate the sigmoid function, right? So this sigmoid function helps the numbers to be between 0 and 1. So why do we need this extra G and R? We like in the normal RNN, we can only have one calculation of the output or the hidden state. Here we have two extra gates. So these two Z and R are actually called weights. Sorry, gates. So they control the flow of information, whether we have to take in the last information or not. So as you can see here while calculating h theta, I believe. So what are we going to do is, when we are going to calculate the previous hidden states into UH, so UH is actually the current weights, and then when we are multiplying these weights, we are also going to multiply that by R. So here R is acting like a regularizer. So R is going to be between 0 and 1. And if R is really smaller, then this weight or this term will be given less importance. What is this term? This term is nothing but the previous hidden state multiply by the weight UH. So we are going to, if R is really small number, then this is going to be very small. And if R is going to be very larger number, this term will be given highest amount of importance. So as you can observe here, this R is going to control how much importance we should give for the previous hidden state, right? How important is the previous hidden state? And then Z also, here we have, and in the next equation, we are going to use Z. So if Z is really high value, then this term is going to be given the highest importance. If the Z is very lower value, then this term will be going to give the highest importance. So here we are just controlling whether we should give the highest importance to the previous output or the previous hidden state or the current hidden state. So H, we are going to calculate H based on the Z. So Z is going to control if we should just output the previous hidden state. We are just going to if we want to give more importance to the previous hidden state and the final hidden state. So that is why this is called gated recurrent units. We are going to have some gates that are going to regulate the movement of hidden states. So if we want to give more importance to the previous hidden state, then neural network is going to increase these weights UZ and WR and UR. Hence, these values are going to be higher. If these values are higher, then more importance will be given to the previous state. Or I think higher, right? Yeah, yeah. If Z and R are higher, then more importance will be given to these previous hidden states. And if they are lower, less importance are going to be given to the previous hidden state, and more importance is going to be given for the current output or current hidden state, current calculation based on the input. Hope you got that. So that is why we have some gates that are going to regulate this movement bit of hidden state vectors. So that is why GRUs are used. Even though these are pretty good, even though they do actually work that very good, even though they do work, they do solve the problem to some extent, but we don't have that much complexity to actually have a have built a very good system that can actually regulate the movement. So therefore, in LSTMs, we have further more gates. We have actually have more gates. So that is why LSTMs are actually used before attention mechanism came. So before transformers came, LSTMs are used. I'm just going to share that. You can actually understand this also. So in the last layer, in the last GRUs, we only had two gates, Z and R, Z and R. Here we are going to have four gates, F of t, I of t, O of t, and this gate, as you can see here. Right? So this is also a sigmoid function. This is also is actually a gate, right? So if you just understand it, what is going to happen? All these are just same as what we have read in the GRU's formulas. We are going to have some weights. We are going to multiply that by x of t. We are going to have another weights UF, and then we are going to multiply that by previous hidden state, and then we are going to have this bias. So all these are parameters that are going to update it during training. So during training, we are going to update all W's and U's and B's, right? And we're going to have the sigmoid function, which is again going to turn this values between 0 and 1, either giving highest importance or lowest importance to each of these metrics. And then we are same for this also, same for this gate also. We are going to have another sigmoid function controlling I think I of t, right? So we are going to have the same calculation but with different weights. And then so what is the main thing is this F gate. See, this F of t is going to control the previous output. So we are going to multiply F of t by the previous hidden state. So if F of t is very smaller number, then less importance will be given to this previous hidden state. So if F of t is very higher, then more importance is going to be given to C of t minus 1. So C of t minus 1 is nothing but the previous hidden state input. So we are going to have this hidden state going through RNN or LSTMs, right? So therefore, if F of t is very high number, more importance will be given to this previous hidden state. And then we are going to multiply again I of t by this that controls the input. So here I of t is going to control how much we should control the input or something, how much we should give more importance to the input. So we are going to further multiply that by another sigmoid function, that is also between 0 and 1. And then if we get to the final h of t, we are going to multiply this function, which is output. This is actually output, a sigmoid of C of t. You can use whatever activation function you want. Right, so let's say if you are doing multi-class classification, you can use softmax, having multiple neurons and all that. So what are we going to do is, but here they use sigmoid. So what we're going to do is at the output, we are going to multiply that by O of t. So O of t is going to control how much a big an output should be, right? So it is going to, or a hidden state should be. How big value should our hidden state contain? So that this is the LSTMs and GRUs. Hope you understand that. So basically, in simpler terms, we are going to have some many more gates that are going to control how much importance should we give for previous hidden states, right? And how much importance should we give for current outputs. That is a basic idea of these LSTMs. And remember, we are going to have multiple blocks, and the number of blocks is going to be the number of time series or the length of series. So now that we have understand how what is the actual idea of trading a or LSTM or GRU. Let's try to build one using TensorFlow. Just go to the last file that we have already developed. This is the program or model that we have developed for stock price prediction. We are just going to change the part of simple RNN and change it to LSTM. LSTM is actually another layer. Let's run it all. Let's see how it performs. I'm just going to remove this. Right, so we're going to have we're just going to run it again. All these files run all. Let's see if we can able to perform better. Let's see if we can able to perform better. The session is starting, so it might take some time. You can also rename it, name it whatever you want. Let's say stock price forecasting. Okay, so as you can see, yeah, the loss actually started. The classic, we have already tried it before, 1,94,000. So let's see how it goes. I'm just going to pause it and see you after training. All right, so we are at the 72nd epoch, and I think we have reached 52,000 loss, and that is a bit higher. But we are getting there very fastly. So as you can see, when we are solving like very huge problems, you can see the difference between RNNs and LSTMs. Stock price prediction, we only have one value at a time, and then it's actually like it is not that complex problem compared to the like actual problems that we are solving, like in like chat GPTs and all that, language models and all. The actual time series problem, if we are solving complex problems, relatively complex problems, we can see the difference by using LSTMs rather than the RNNs. So that's it. So hope you can understand. And then thank you for watching, and I'll see you in the next video.